Welcome to the beginning of ECE 261. We start with Coulomb's law, basic Coulomb's law, which is used to describe classical charge interactions. Now, these interactions allow us to define the energy associated with groups of charges, and that energy really provides the basis for all circuit analysis. We begin with a single positive charge in space. We introduce a negative charge. And we know that there will be an attractive force that pulls the negative charge towards the positive charge as indicated in the diagram. We see the formula that describes that attraction, and that's F2. It's the product of the charges divided by the distance between the charges, R12 squared, multiplied by the unit vector. And this is all described very clearly in the next slide. Here we have it in a little more descriptive detail. We again have Coulomb's law, as you can see, F2, the product of the charges, divided by 4 pi epsilon naught R12 squared times the unit vector A hat 12. R12 is the magnitude of the vector R12 as indicated below, and the unit vector is the R12 vector divided by its magnitude. That defines the attractive force F2. Since Q1 and Q2 have opposite sign, the force is shown as directed. However, the positive charge, Q1, is also attracted to the negative charge, Q2. And if we call the force F1 on Q1, we note that F1 would be negative F2. This is completely analogous to what occurs in gravity. In the description of Coulomb's law, we're still missing one term, that's epsilon naught, and epsilon naught has been measured very carefully as shown in the slide. The other thing that's interesting is the exponent of the distance, R12, and it's to the power of 2 measured to 1 part in 10 to the 9 by Plimpton and Lawton in 1936. So this is the fundamental description of the force between two charges, but there's still the issue of how we actually represent that force in terms of visualization. So now we see a model here of something red and something blue connected by a rubber band. The red knob represents a positive charge, and the blue cap to a pen represents a negative charge. You can see from the picture that there's an attractive force, and I've modeled that as a rubber band in tension. Clearly, the energy stored in the field, or the force, is represented abstractly by the tension in the rubber band. So now we actually have a visualization of the force field for a fixed position of the negative charge in space, and I'm actually feeling a pull by the rubber band on the blue cap, which is like the attractive force mechanically analogized pulling into the red knob, which is the positive charge. And there's energy stored in the field. You know that because the minute I let go, this blue cap is going to accelerate into the red knob.